light feels continuous in daily life. A sunrise brightens gradually, a room lamp fills space smoothly, and a radio signal seems like a steady wave. For centuries that intuition shaped science. But at the most fundamental level, electromagnetic energy is exchanged in discrete packets called photons. A photon is the quantum of the electromagnetic field, meaning it is the smallest unit in which that field gives or takes energy in interactions. This applies across the full electromagnetic spectrum, not only visible light. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are all different frequency ranges of one unified field, and photons are the common unit across all of them. That is the first big shift. Light is not just a smooth wave spread through space, it is also quantized in how it interacts with matter. Photons have a compact set of defining properties with enormous consequences. They are massless, which means they have zero rest mass, not merely a tiny value. Because of that, in a vacuum they always move at the speed of light. There is no valid physical state where a photon is parked or slowly cruising. Photons are also electrically neutral and belong to the boson family. Being bosons matters because many photons can occupy compatible quantum states, which later enables coherent effects like laser beams. Most importantly, photons are force carriers for electromagnetism. In modern physics language, electromagnetic interactions are mediated by photons. So when atoms bind, charges repel, or antennas transmit signals, the underlying interaction structure can be described through the electromagnetic field and its quantum excitations. The photon is therefore not just a light particle, it is a core actor in how nature communicates force. To see why this idea was radical, we need the historical tension. Classical physics treated light as a wave, and that model worked very well for many effects such as interference and diffraction. But around the turn of the 20th century, some measurements refused to fit a purely continuous energy picture. Max Planck studied thermal radiation and the equilibrium between matter and electromagnetic radiation. To match observed spectra, he proposed that energy exchange in material oscillators occurred in discrete equal chunks, not arbitrary values. Planck initially framed this as a constrained mathematical move, but its meaning ran deeper. Nature might quantize energy transfer at a fundamental level. This was uncomfortable because it broke with the smooth continuity expected by classical theory. Yet the data demanded it. Planck's step did not finish the quantum story, but it introduced the quantization principle that made photons thinkable. Einstein's photoelectric analysis pushed quantization from a technical fix to a physical claim about light itself. In the photoelectric effect, shining light on a metal can eject electrons, but the pattern is strange from a classical intensity-only view. If light were just a continuous wave delivering energy gradually, enough intensity should eventually free electrons even at low frequency. Experiments did not behave that way. Below a threshold frequency, no emission occurred regardless of intensity. Above threshold, electrons were emitted, and their energies tracked frequency. Einstein explained this by proposing that light energy arrives in packets, each packet tied to frequency. An electron absorbs one packet at a time. If that packet lacks the minimum required energy, nothing happens. If it exceeds the threshold, emission occurs. This model directly linked light frequency to discrete interaction events and provided compelling evidence for photon-like behavior. As the concept matured, the term photon was adopted and then reinforced by experiment after experiment. But one subtle point is crucial: photon theory did not delete wave behavior. Interference patterns and diffraction remained real and measurable, so physics could not simply replace waves with little billiard balls. Instead, quantum mechanics provided a broader framework where both aspects appear in consistent ways. Light propagates with wave-like behavior described by field amplitudes, yet detection and energy exchange often occur in localized, countable events. This is wave-particle duality, but it should not be treated as a vague paradox slogan. It is a precise statement that different experimental arrangements reveal complementary features of one quantum object. The photon concept survived because it accurately predicted where classical intuition failed while preserving the successful parts of classical wave optics in appropriate limits. A concrete way to internalize duality is the low-intensity interference setup. Send very weak light through an interferometer or double-slit apparatus, and detections on the screen appear one by one as localized points, particle-like events. But after many events, those points build an interference pattern that only wave-like amplitude structure predicts. Individual outcomes are discrete, their statistical distribution is wave-like. This is not a contradiction inside quantum mechanics, it is the expected behavior. The theory predicts probabilities for where a photon may be detected, and repeated trials reveal that distribution. In this sense, photons forced physics to embrace probabilistic description at fundamental scales. Not because of ignorance in measurement alone, but because probability amplitudes are part of the core formalism. The practical implication is profound. We gain predictive power by abandoning the demand for a single classical picture in all contexts. In the Standard Model, photons are embedded through gauge symmetry, which is one of the deepest organizing ideas in modern theory. Gauge symmetry means the equations describing fields have internal redundancies that preserve physical predictions, and those symmetry requirements constrain what kinds of particles and interactions can exist. The photon emerges as the gauge boson associated with electromagnetism. This framework naturally encodes its key traits, zero electric charge and zero rest mass, consistent with long-range electromagnetic force behavior. Unlike massive mediators, a massless carrier supports interactions over unlimited range, which matches the observed reach of electromagnetism. So the photon is not merely an empirical patch to explain special experiments. It is structurally required by the symmetry architecture of our best-tested particle theory. That makes it simultaneously a measured object, a theoretical necessity, and a bridge between mathematics and physical reality. Once photons were understood as quantized field excitations, technology advanced in ways that would have been impossible under a purely classical interpretation. Lasers are the iconic example. Because photons are bosons, large numbers can occupy coherent states with aligned phase and direction, producing intense, highly controlled beams. Coherence enables precise cutting, surgery, metrology, timing standards, and optical instrumentation. In microscopy, photon-based techniques push resolution and contrast, allowing biologists and materials scientists to image structures with exceptional sensitivity. In photochemistry, quantized light-matter interaction clarifies why certain reactions trigger only under specific wavelengths. Molecules absorb photons in energy-selective ways. These are not isolated inventions unrelated to theory. They are direct consequences of the photon framework applied to engineering. The practical world of modern optics is effectively a long proof that quantum light concepts are not abstract philosophy but reliable design tools. Communication systems provide another major domain where photons dominate. Optical fibers carry information over long distances with low attenuation because light can be guided efficiently through transparent media. At scale, global internet and telecom infrastructure depends on this photon transport architecture. Quantum communication takes the story further by encoding information in quantum states of individual or correlated photons. In quantum cryptography, especially key distribution protocols, measurement itself becomes part of the security mechanism. Intercepting a quantum signal can disturb state statistics in detectable ways, exposing eavesdropping attempts. This reframes cybersecurity from purely computational hardness toward physically testable guarantees. Photons are ideal for these tasks because they travel fast, interact controllably, and can be generated and measured with increasing precision. So the same quantum object that challenged old physics now underpins both everyday connectivity and frontier secure communication paradigms. Photons are also central in quantum computing research, although their role varies by platform. In some architectures they act as flying qubits that transfer quantum information between nodes. In others they mediate entanglement generation or measurement processes that connect stationary qubits. Their low environmental interaction can preserve coherence in transmission, which is valuable for scaling distributed quantum systems. At the same time, controlling deterministic photon-photon logic remains technically challenging. So many designs combine photonic channels with matter-based processors. This hybrid direction highlights a broader point. Photons are not only historical triggers of quantum theory, they remain active components in the attempt to build quantum technologies that outperform classical systems for selected tasks. Even where full-scale quantum computing is still developing, the photonic toolkit already shapes experimental strategy, hardware interfaces, and error-aware architecture design. There is also a conceptual lesson in how photon theory evolved. Science did not progress by mocking classical ideas and replacing them overnight. Classical wave optics remains valid and incredibly useful in regimes where quantum granularity is not the limiting feature. What changed was scope. Quantum theory expanded the explanatory range to include discrete interaction events, threshold behaviors, and probabilistic outcomes inaccessible to older models. This layered evolution is a pattern across physics. Successful theories are often recovered as approximations inside broader frameworks. The photon embodies that pattern perfectly. It preserves wave propagation insights while adding quantized exchange and field-based particle interpretation. For learners, this helps avoid a common trap of choosing one image too literally. The goal is not to force nature into one metaphor. The goal is to use the right formal description for the phenomenon and scale at hand. So if we compress the full story, a photon is the quantum of the electromagnetic field, massless, neutral, and always traveling at light speed in vacuum. It behaves in ways that reveal both wave-like propagation and particle-like detection, unified through quantum mechanics. Historically, Planck introduced quantized energy exchange, Einstein used light quanta to explain the photoelectric effect, and later theory embedded photons in the symmetry structure of the Standard Model as electromagnetic force carriers. From that foundation came major practical revolutions: lasers, advanced imaging, photochemical control, optical communication, quantum cryptography, and photonic quantum systems. The photon is therefore not a niche detail in physics vocabulary. It is one of the clearest examples of how a precise, initially counterintuitive concept can reorganize both scientific understanding and technological civilization. If you found this helpful, please like this video and subscribe for more explainers.